started the recording. For the new members who are joining this session for the first time, we normally record the session so that if you haven't managed to join, you should be able to see the recording. This is our 6th session. We've already covered 5 sessions from different trainers who have come in and shared their knowledge. And we also encourage you guys to come up with topics and share your knowledge in different domains that you feel you can share knowledge. I believe we all have something that we can share with the rest of the team. And that's why we have this platform by Life Technology, so that we as network engineers, we can share the knowledge that we have with the other engineers. We can empower them. We can also inspire the new engineers who are starting their journey in network engineering, so that they understand what they need, they learn the key technologies, they learn the best practices that they need in their career growth. Let me first appreciate those who have joined on time. Thank you so much for taking your time to join this session. And I also want to appreciate David Muita, for taking up this topic. MPLS, which is a protocol that you will never miss on many service provider networks. We've talked about OSPF, we've talked about ISIS, we've talked about BGP, and now we are talking about MPLS. But remember, MPLS doesn't work alone. It builds on top of those other protocols that we've discussed. That's why we started by discussing, for example, we discussed about subnetting, we discussed about OSPF, we've discussed about ISIS, and now BGP. Once you've deployed these protocols on your network, you now go ahead and deploy MPLS on top of it. So today we are glad to have David Muita take us through MPLS. This session will be purely a theory session, and then later we will have a lab session where we can now discuss how you can configure MPLS on your network, both configuring it and also troubleshooting it, because it's not just a plug and play. You need to configure and also troubleshoot MPLS or any other protocol on the network. Some rules: I hope you keep your mic muted. If you have a question, always raise up your hand so that we don't have a lot of distractions, and give the instructor time to discuss a topic before you can distract with the questions. So just keep your mics muted. Allow David to do the presentation. He will have Q&A sessions in between so that he can address some of the questions that we'll be having as we continue with the session. Thank you so much again for joining. Let's make it more interactive. Let's engage with each other and ask those questions on the chat also as we continue with the presentation. David, you can take it up and take us through the MPLS protocol.
All right. Thanks, Martin. Just some quick checks. How is my audio?
From my side, it's okay. Others can also confirm from their side.
Okay.
And also, if you can see the screen, confirm you're able to see the screen. All good, David.
Okay. Thank you so much. Good morning, good afternoon, good evening from wherever you're joining us from. I want to appreciate all of you for taking the time to join us on this beautiful Saturday afternoon, I can say, because I'm in Kenya. So I'm hoping wherever you guys are, it's also a beautiful day, and the day is coming along very well. My name is David Muita, and just like most of you guys, I am a networking student. I'm still learning, but today I am so glad that I'm going to take you through one of my favorite topics, that is MPLS. Now, I recognize the fact that people who have joined this live session, we have those who are beginners, we have those who are intermediate in terms of networking, and also we have those who are, I can say, expert. So I'm doing this presentation having that in mind, that we have so many people who are here of different levels of understanding of networking. So if you guys are here, you're in the right place, and I'm excited to take you through MPLS. Now, before we even talk about MPLS, which stands for multi-protocol label switching, I just want to show you what we'll be covering today, if time allows, and I'm hoping time will allow us to, cover whatever I have prepared for us. So first, we'll talk about how was life before MPLS. We'll talk about traditional IP routing, its shortcomings, what are or what are the typical usage, because currently, even as we speak, we still have networks that run without MPLS. And then thereafter we'll talk about life now after MPLS. What are the benefits of MPLS? What are the terminology that we need to know whenever we're dealing with or we are working in an environment that MPLS is deployed? We'll get to talk about label distribution protocols, understand how labels are distributed. And then we'll touch about the two main applications, I can say, for MPLS, or how MPLS is applied within our service provider network, or even very large enterprise networks. There is where we'll talk about L3 VPNs and then L2 VPNs. Then lastly, we'll touch about MPLS traffic engineering, what it is, what are the benefits of MPLS traffic engineering, and in short, it's called MPLS TE. And then we'll have a Q&A session. So the goal here is to cover this within 2 hours. I know today is a Saturday, and for the football fans, more specifically the Arsenal fans, I would like to let you guys have enough time, to prepare. If there's a jersey somewhere that you need to iron or do something about it, then I would love to give you time to do that. So let's get straight into it and get to discuss about traditional routing. This is basically IP routing. So as most of us may be aware, traditional IP routing is basically routing that involves, decisions are made by a router or L3 devices which have routing capabilities, where a decision to forward packets is based on destination IP addresses, purely IP addresses. And then I'm glad Eve did take us through subnetting in our very, very first session. So therefore, we have a fundamental or a basic understanding of what IPs are, how they are subnetted, how they are, applied. So when I say that traditional IP routing was based on destination IP addresses, then most of us should be able to relate to that. So basically, what was happening before MPLS and what is still happening even after MPLS, because like I mentioned, we still have networks that are not running MPLS and they're just working fine. So this is what happens without MPLS. So a packet arrives in a router. So what happens is a router looks up its routing table and finds the match to that destination. Okay, and then it chooses this next hop independently. Then after that, it forwards that decision to the next hop. Okay, I'll allow me to just Martin mentioned that this is going to be a theory, but we're going to do we're going to have a practical approach of this. So just assume these are our two routers. Okay, so the packet arrives in this router. So what router one does, it does a routing lookup and then finds the match to maybe the destination here is 10.1.1 dot 3, which is here. So after finding that match in its routing table, it forwards that particular packet to the next hop. So router 2 does the same thing. It forwards that packet to the next hop, which happens to be our destination. So therefore, what happens is that for traditional routing, IP lookup is done in every router, and in this case, a hop here is another name for router. We can substitute hop with the router. So every router does lookup, and then it finds the matching prefix for that particular destination IP address, and then it forwards that packet to the next hop. I did do an explanation here, which I've just summarized. So the outcome of this particular behavior, where we're using traditional IP routing, is that we have heavy processing at every hop, because assuming this router here has about 1K, it has 1,000 routes, it has another maybe 2,000 routes. It has to look, and when I was preparing for this session, I found that what happens is that the router first of all analyzes the entries in its routing table from the beginning all the way to the end. So imagine you have 1,000 routes where this router has to scan and be able to find out which one is the longest prefix match for me to forward this packet to. So that can be CPU intensive. I don't want to use the word labor intensive. It can be CPU intensive or resource intensive, and it can be a bit slow. So when we proceed, I will be able to tell you that nowadays, luckily for us, this is no longer a problem. But still, MPLS is the most preferable whenever you're running a very big network. So in traditional IP routing, path selection is based on interior gateway protocols like ISIS or SPF or BGP. We could even have a situation whereby you use static routing, although that doesn't scale very well when you have a very large network. So therefore, the preferred one, that's why I've not included it here, the preferred one will be the IGPs that we have SPF, ISIS, or BGP. Now, for the lovers of Cisco, or for the fan of Cisco, I haven't included EIGRP simply because it's a Cisco proprietary, and therefore, if you are in a multi-vendor environment, so you'll not be able to use EIGRP. But in case your network is purely Cisco, then of course you can add EIGRP to this list. But I've just chosen to go with SPF and ISIS because, and also BGP, because these are open standard. Every vendor, be it Huawei, Cisco, Juniper, understands these three languages here. Now, again, for traditional IP routing, path selection, or where should I send my packet is chosen based on the cost, or some literature will call it metric. And basically, this is the shortest path. It doesn't care about bandwidth. It doesn't care about resources, are they available or not. As long as it's the shortest path, then, for example, here in router 1 will just send that particular packet, and then router 2 will also send it this way, regardless of whether there is congestion in that link or no congestion. Now, when it comes to traditional IP routing, in terms of influencing which path or the next hop an IP packet will take, you have very limited control. I'm not saying it's not possible. It is possible when you talk about policy based routing, PBR. So it's possible to use PBR to control, but again, that is not very scalable, because you're going to have to do configurations almost in every router along the path for you to be able to influence how traffic flows from point A to point B. Let me clean this up. It's a bit messy. So now we've already spoken about the default behavior of IP packets in just a normal or traditional IP routing. Let me say the word traditional does not mean old. It simply means this is how things were done or things are done without MPLS. Okay, so don't say it's an old technology. No, it's not. It's still being used or applicable today. So the default behavior is that traffic flow follows a shortest IGP path based on cost or metric. Now, moving forward, we have the basically MPLS. So imagine I've already spoken about this a few minutes ago, where you have large routing tables, and then you have to do IP lookup. So that could be, lead to high CPU usage and therefore slow down your network. And then it means that sorry, it means that when you have your core network, full routing has to be done inside your core network, which again could be labor intensive in terms of someone who has to log in and do all those configurations and be able to influence traffic. The way I said, we have limited control of how our traffic flows when you're using traditional IP routing. And then we have the typical usage of traditional IP routing without MPLS. It's still used in enterprise networks, where you'll find the enterprise network, the network engineers for some reasons are running IP routing because maybe for them it's a small it's a small network, or maybe because of the cost that comes with MPLS. As for those who joined early, Martin was telling us, so they will prefer to use IP routing. We also have small ISPs. Apologies for the word small, because I didn't get the best word to describe it. We have small ISPs that still use are still actually using IP routing, and then now the internet, as we know, BGP is the protocol that runs the internet, and therefore BGP is still used, and it's the only exterior gateway protocol that we know. And for those who have configured normal BGP, then you know very well that it uses IP routing. There's no MPLS. Although as we move forward, we'll be able to talk about another flavor of BGP, which is MP BGP. Simply means multi-protocol BGP, specifically multi-protocol IBGP. This is what we'll be talking about when we tackle L3 VPN. Apologies for my very bad handwriting in this screen, but I hope you get the point. So that is a brief introduction about traditional IP routing, which was not the focus of this session. But since we are talking about multi-protocol label switching, it was only ideal to talk about traditional IP routing before we go ahead and talk about MPLS. Any questions? Martin confirmed that I was audible, and at no point did I break.
Yes, very audible, very clear. We are
Okay,
following
thank you.
Hello, hello, Sir David.
Yes, sir.
Yes, before, first of all, from the beginning, when you said traditional routing and all of that, I just wanted to get
Okay.
it right. So that means if you don't have too much entries in your router, you don't need MPLS if your network is small. Is that correct?
I would say no and yes, Elisa, because look at this way. Why do we have MPLS? And that's what we're going to cover in the next session. So the decision to use MPLS or not use MPLS purely depends on what are your network needs. What are your network needs? So I'm simply just taking you through all those options, all those flavors for you to decide when to use it. But yeah, in case you have a very small network, Therefore, I would not really see the need as to why you'll run MPLS within your network. But if you have a very large network, then I would definitely recommend you to use MPLS.
Okay, thank you. I just wanted to get the right way to use it, if the need, why you need it, and when you don't need it. But it's fine. Thank you.
Yeah, we'll cover that very shortly. When you talk about MPLS, why we need MPLS, and where MPLS is not required.
Thank you, Brother David.
No worries. Okay, so let's get into the topic of the day. This is why you guys are here. We've been preparing this with Martin for, in full disclosure, we've been preparing this since March. We were to have it before April, but we saw it best for us to have ISIS, and then we have BGP, and then we come and have the virtualization that happened 2 weeks ago, before we can come and talk about MPLS. The reason is that MPLS requires very many components for it to be able to run. You need an IGP, you need MP BGP. We'll talk about that very soon. That's why we had to wait for those topics to be covered, so that when it comes to MPLS, now we have a better understanding. When you talk about running ISIS or SPF within the MPLS core, or some literature will call it MPLS cloud, same thing, depending on how you're using it. So what is MPLS? First of all, we have to understand what it means in full. So it's, as most of you have already seen or are aware, it's multi-protocol label switching. So the key here is it's a multi-protocol technology, and then it uses label to be able to forward packets. And therefore, from that definition, we can say that it's a high-performance packet forwarding technology that you'll mainly find in service provider and large enterprise networks. And then it moves traffic efficiently across a network. And we'll get to see about that efficiency in a very short while. Now, we're talking about traditional IP routing, which uses IP packets, and basically you just look up the destination in a router, and then you forward that packet to the next hop. MPLS is actually using labels to identify packets and switch them, meaning you identify a packet, so there's an incoming, there's an outgoing, as we will see in a short while, whereby the MPLS will add a short identifier, which is called a label, to those packets. So routers will now, after doing that, they will forward packets based on those labels. And what you get here is that it makes forwarding faster and enables advanced traffic engineering and VPN services. This is a topic that we'll cover shortly. Okay, and now the reason as to why MPLS is better than IP routing is because one of the many advantages is because it will skip, because IP routing lookup is a very complex process. So MPLS will skip those complex lookups in routing tables at every stop, and which will make data routing faster. Now, in bracket here, I said it's not an issue nowadays because we have very powerful hardware nowadays that will be able to forward packets quickly, even without running MPLS. But this is an issue. No, not an issue. This was not the case. Sorry, this was not the case a few years ago, and that's why we are still talking about its efficiency, and it's faster compared to traditional IP routing. Now, the reason as to why MPLS has that multi-protocol in its definition is because it can work. It can work with various network protocols. Basically, it can encapsulate packets of various network protocols. When you talk about, for example, when you talk about data link protocol, which is basically layer 2, for those who know their OSI model basics, we have layer 1, 2, 3, all the way to layer 7. So when you talk about layer 2, The modern standards of layer 2 is, of course, the Ethernet, where we have Ethernet over MPLS for layer 2 VPNs. And then we have the legacy or the traditional technologies, which are asynchronous transfer mode. We have frame relay and PPP. So that's why we have that term multi-protocol. It means, irrespective of what you're using as your layer 2 protocol, MPLS will still be able to work and function very well within your network. And nowadays, it's very rare to see these legacy technologies, that is ATM, frame relay, and the triple P. But they were used before. As you can see, MPLS is something that has been here with us, I think now 20, more than 20 years. It's actually 30 years, right? Almost 30 years. So since 1997 is where MPLS was introduced. Now, in terms of where MPLS belongs, when you talk about in difference to the OSI model, it lies between layer 3 and layer 2. And that's why in most literatures, we'll find that MPLS is called, is referred to as a layer 2.5 protocol, simply because that's where it's found. I don't have a graphic of the OSI model, but you can do some further research. You'll be able to know why it's called layer 2.5. So moving forward, we have a simple analogy for you to be able to understand how MPLS works. So you have think of a normal IP routing, like mailing a package, where in every post office you go, they have to read the full address each time and know that this package is supposed to be sent to Martin, this package is supposed to send to Viola, supposed to be sent to Rachel or Dixon. Now, the process of reading the full address, for example, PO Box 121, Nairobi, or 121 Dubai, or it's tedious. So what MPLS does is that particular package will get a very special sticker, which is in this case a label, and it's easy to read a label because it's numeric. It doesn't have any other thing. It's just numeric. If it's 3 is a special one. If it's 20, if it's 40, it's 50, it's easy to read. So once that package of yours has been assigned a particular label, then those people who are responsible for carrying the courier services were responsible for delivering this particular package. You just be able to know, for label 20, I'll have to deliver it to so and so. For label 30, I have to deliver it to so and so, instead of reading the entire address. Now, another thing about MPLS is that it follows a predetermined path, and we'll see how that happens in a short while. It follows a predetermined path, meaning before this packet is sent from, for example, before this packet is sent from point A all the way to point B, this path is already determined, okay? Therefore, it becomes very quick and efficient to be able to send the packet from the source to the destination, okay? Lastly, no, not lastly, but this is how the MPLS label format, the label looks, the format is itself. So the MPLS header is a 32-bit header, okay? So inside that particular 32-bit header, it's divided into 4. Now we have the label itself, which is 20 bits. This is now what we're actually talking about. And then we have the XP bits, which is 3 bits. And then we have the S, which means for stack, and then TTL, which means 8 bits. Now, the details of those labels are here. So the first one, which is 20 bits, now this is actually the actual MPLS value. So whenever, if you go back to the simple analogy that we had, if that sticker is assigned to that particular package, the actual value of that sticker is now 20 bits. Now that is the label itself. Remember, this is there's an MPLS header, and then inside that we have four categories. So number one is label, and the range is between 0 to over a million. Now I took so for labels 0 to 15, these ones here are reserved for special purposes. So you rarely see them being assigned, but you can see them being assigned. For example, Huawei will assign label number 3, which if I'm going ahead of myself, it means it's an implicit null. We'll be able to see those ones in a few. So in Cisco, how you can be able to check the the mean and maximum labels in Cisco gear, you use this command in green, and then in Huawei you use the command in green. So for Cisco it will show you a million, and then for Huawei it will show you slightly above that. I'm not sure about Juniper and other vendors, but I'm assuming since MPLS is not vendor specific, then they could be having the same REB ranges or slightly out of or slightly different from what we're covering here. But for the lab that I'll be using the next time we have this particular session, and even the one that I'll be using here, because I've prepared a very small lab to be able to just show you a few things as we move on. It's a multi-vendor lab that has Huawei and Cisco. So what this label does here is that it identifies the forwarding equivalence class. And then this is what a fake means, or a forward equivalence class. It's a group of packets that are forwarded through the network in the same way, meaning they use the same path and the same forwarding treatment. So what happens is, instead of making a forward decision at every hop based on the IP header, MPLS will classify into a fake at the ingress, classify packets into a fake at the ingress label switch router, that's LSR. We'll be talking about terminologies in a few, just bear with me. Then a label is then assigned to that fake, and subsequent routers forward packets based on that particular label. So fake is basically a group of packets that are forwarded through the network in the same way, meaning these packets will use the same path and will use the same forwarding treatment, as we'll be seeing in a few again. Now, labels are used by routers to forward and perform these three MPLS operations. We have push, swap, and pop. Just to tell you what they mean, because we'll be covering them in a few. Push is just assigning a label. Swapping is you remove a label and add another one as before you forward it. And then popping means removing the label completely before you forward the packet to its destination. Number two, we have the EXP bits, which is simply traffic class. This is the modern way of calling them. Is a traffic class. And for those who understand a bit of QoS, this is actually used for quality of service. Now, when it comes to the experimental value or the traffic class values, in terms of quality of service, whenever you see a 0, it basically means there is no QoS actually. It's just best effort. This is basically for data. Whenever we see 1, it's meaning it's low priority or bulk transfers. 2 is excellent effort, which is better than best effort. Now, most of us are accustomed to these particular values, number 4 and 5. When it comes to QoS, the most talked about things are the voice and video. And when you're doing the configurations, now these labels here, let me say, they are not, this is not like gospel truth, or maybe you have to use them, but this is the standard that has that has been put out there for anyone who wants to use to apply quality of service within their network. So for them to refer, you just have to refer, so that whenever we see a 0, we know it's the best effort. Whenever we see 4 or 5, 4 is video, and then for 5 is voice. Number 6 and 7 are actually special ones. These ones here, you cannot be able to assign them to your network, because they are simply used by to control network. Number 6 is basically for routing protocols, e.g. ISIS or SPF. And then for number 7, again, it's just for highest priority control traffic. So the last one here, they are reserved basically for whatever happens within the network, because routing has to take place, and therefore the experimental bits that, or the traffic class bits that are assigned for those specific tasks are number 6 and 7. The next one will be the S bit, which basically means bottom of the stack, which is 1 bit. It indicates whether the label is the last or in the stack or not. So if you see a 0, you'll be able to say that there's another label, or there are more labels below. But if you see a 1, it simply means that this is the bottom label, and therefore there's no any other labels. Now, the MPLS label, the MPLS header also has a time to live, just like we have the time to live in IP, the normal or the traditional IP routing. It has time to live, and its work is simply to prevent loops within your network. So if the TTL is 0, then that packet is dropped. If the TTL is not 0, then it propagated. So this one here prevents the packet from, for lack of a better word, moving within your network infinitely without ending. Therefore, that is the work of that particular section, or that particular bit when it comes to the MPLS header. So that portion of the TTL is simply because it is used for within your network to prevent loops, and you'll basically see this when it comes to your trace route operations. That's where that is applied. Now, just as a side note, in MPLS, the label 3 represents the implicit null, and this simply means that it tells the second to last, as we'll be seeing in a short while, the second to last router to remove or pop the top label before passing the packet to the final destination router. Now, this is used to save the final router a lookup step. So basically, label 3 implicit null, it means penultimate hop popping, which simply means second to last. Now, it's a lot of theory. Very soon I'll be showing something in a lab just to relate this. Now, we have a concept called MPLS label stack, whereby you can have more than one label stacked together. And this is the common behavior when it comes to, L3 VPN. We have the outer label, which is used within the MPLS core, and then we have the inner label, which is used by the egress PE. And then now we have the IP packet itself. So after all these labels have been popped, now the IP packet is forwarded to the destination without any labels. So basically, we'll be able to see a label stack. This is a theory, but with a practical approach, and I'll be doing my best to ensure that all these concepts are understood. So, why do we use MPLS, or what are the benefits of MPLS? Number 1, traffic engineering. And whenever you see the word traffic engineering, I want you to think about how to control your traffic. Okay, we saw with normal or IP routing. This is possible, but we can use policy-based routing to be able to influence how traffic moves within your network. But that is not very scalable. It's not very efficient. That's why MPLS was introduced, and it gives you a lot of control as a network engineer to be able to decide or be able to influence how traffic engineering is influencing or controlling how traffic moves within your MPLS network. And what determines how to influence that traffic is actually the customer needs. What does the customer need? The customer needs a path that has low latency, and therefore things like slowness or lags and are catered for. A customer will need a path that has enough bandwidth. The interface has enough bandwidth to be able to push whatever traffic, whatever data that the customer wants to push. So therefore, when it comes to traffic engineering in MPLS, you have a very good or let me say a working environment for you to be able to control traffic. Now, this is basically forcing traffic to use a particular path as opposed to another path. So what you get with MPLS traffic engineering is you avoid link congestion. You're able to reserve bandwidth, as we saw earlier. Traditional IP routing uses IGP. Basically, shortest path is chosen. But in MPLS, as we are all aware, the shortest path is not always the best or the optimal path. That's why traffic engineering comes in and be able to give you the control over how your traffic is supposed to move from point A to point B. As an example here, you can have customer A using a path that has low latency, and then customer B uses a path that has high bandwidth. This is possible when it comes to traffic engineering. Number two, we talked about where MPLS is applicable shortly, but now one of the benefits is that you're able to use MPLS and apply L3 VPN. And how this works is that you have, let me say you have about 2 customers. They have come to you and they have asked you to be able to. Now this is where I come up with the lab. If you allow me, this is where I come with the lab. Now I hope my screen is visible. Okay, so Martin, you confirm? No, you are my.
Yes, it is visible.
Okay. Now, so how L3 VPNs looks like. So first of all, let me just explain this lab here. We don't want to do any configurations, guys. We'll do it in the upcoming session. But for now, just bear with me because this is what I'll be using from here on just to explain a few concepts. So now you have this is the initials here for UG means Uganda. For those who are in Uganda, you're well represented. KE means Kenya. TZ means Tanzania. ZA means South Africa. So Martin Modiba and your guys were represented very well here. Djibouti means, DJ means Djibouti, and FR means France. So basically, you have these 2 customers here. No, that's not what I wanted. So we have these 2 customers here. And the blue routers are Cisco. The other ones that look like dark blue are this one here. This one here is Huawei. This is Huawei. This is Huawei. Anyway, so we have a customer in Uganda who wants L3 VPN services to be able to access their branch in France, for example. And then we have another customer, assuming we have another customer again in Uganda. We have another customer in Uganda here, another customer in France. This is customer 2. So these customers would want to communicate with each other, okay? And these customers here will want to communicate with each other across your MPLS or service provider network. And then these customers are using 10.10/024 network. All of them are using this network. So for us to be able to give these customers the L3 VPN services that they need, we'll be able to do that by using MPLS L3 VPN. That's where we create VRFs and assign each customer VRF, and then we do the configurations. Now I'm moving ahead of myself here. So basically that's what it means. Let's go back to the slide, and then we'll come back here. So this is where L3 VPN is being used. Again, another use could also be L2 VPNs. Benefit number three, sorry, is that faster forwarding. We spoke about this, that it's easier for you to forward a packet based on a label than doing an IP lookup. And then we saw this one here, the longest prefix match, which is the IP lookup, how IP lookup works is very complex. But when you use MPLS label, it's a very simple because it has a fixed length, whereas for longest prefix match, it has to be a longest prefix match. You can have about 2 or 3. So the router has to first of all look up in the routing table, identify those 3, and then pick the best, which is the longest match out of those 3. That can be very slow, as opposed to MPLS, we just look at the label, which is a fixed length of 20, and then it makes a decision to forward that particular traffic. Now, the reason as to why I say that this is not really an issue nowadays is because we have something called ASIC, that is application specific integrated circuit, which nowadays enables packet forwarding, routing, and security filtering to be done at a very high speed, same as you be using MPLS. It's as if you're using MPLS, but still, if you ask me, if you are running a very large organization or a large network, especially service provider network, then please go the MPLS way. Okay. Number 4, we have network segmentation. So think about VLANs in L2. Now we have MPLS. You are able to have within this network of viewers here, within this MPLS network, you're able to have multiple customers who actually use the same IP, private IP addresses, that is, to be able to coexist within your network. And unless explicitly configured, these customer routes would never leak into each other. That's how MPLS is, L3 VPN and even L2 VPN is designed. But so that is a benefit that we also get when it comes to MPLS, that you can have thousands of VPNs without VLAN constraints. You can have overlapping IP spaces between customers. And an example is you can have 2 customers using this particular IP address range with no conflict, because how they are configured, they are within our MPLS or service provider network, how they are configured. They're configured in such a way that these particular 2 customers, their routes are never leaked, or there's no conflict within our network. Number 5 is we have better QoS enforcement as opposed to the traditional IP routing, and this is by the fact that within the MPLS label, the MPLS header, sorry, we have the traffic class, which was 3 bits, if you remember. So those 3 bits are be able to leverage that and be able to classify classify traffic in terms of, is it a voice traffic, is it a video traffic, or do we have mission critical traffic that we will need to prioritize over the other? Because basically QoS, just to digress a bit, QoS is giving different treatment to different classes of traffic. How you'll treat voice or video is completely different to how you'll treat normal browsing. For example, if you want to go to and read a newspaper online, you will not prioritize that traffic over a voice customer who requires that latency should be less than 150 millisecond, jitter should not be more than 30 millisecond, so that is very possible in MPLS, because looking at the header, it has been able to be allocated 3 bits purposely because of QoS. And the next benefit here, I think I have about 10, is fast convergence. I think we've spoken about fast forward, how fast it is to forward or to switch labels within the MPLS core when using MPLS. And then what that offers you is that you also have fast convergence and protection. And basically, this is something that you get to have when you're doing MPLS traffic engineering, where you're able to leverage the use of fast reroute. And then for the new technology that is currently being used, but not at a large scale, is segment routing. So in MPLS, you're able to do configurations and have backup path. As I said, the path from point A to point B is predetermined. Again, if I use this particular topology, if I want to, if this customer here, this customer and this customer belong to the same VRF, as you can see, the name is Amani. Now, I was a bit biased here. I gave this name my son's name. So for those who are Kenyans, you know what Amani means. For those who are not Kenyans, who don't speak Swahili, Amani simply means peace. So let's go back to the topology. So if this customer, that is Amani CE10, wants to communicate with the Amani CE13, now how the packet will be moved within this particular MPLS, that part has already been determined. Now, we can decide and say that this packet will move, will use this path as the primary path, and then come and decide again and say, for the backup path, it will use this particular route. So in your configuration, what you do is you configure all that in this PE. Okay, so you say this is the primary path, this is the secondary path. All these paths here are predetermined, and they're actually valid path. So in the event this particular this particular link here fails, so traffic with the MPLS, we're able to achieve less than 50 millisecond switching, which is very fast, as opposed to when you're using traditional IP routing without maybe the use of BFD. When a link goes, assuming you are running SIS here without MPLS, when this link goes down, for reconvergence to take place so that this traffic comes back here, it takes a bit of time. And today, even a 1 second flap, for those guys who are working in any financial institutions, with fintech now coming into place, any flap that happens for 10 seconds or even less than 10 seconds, the revenue loss is quite significant. So that's why, BFD is able to do that, but then again, MPLS can also do that much faster, where you achieve, like we said here, you're able to achieve a failover that is less than 50 milliseconds. So what you get here is that you get a much faster convergence as compared to IGP. Number 9, you have a clean code design. There's a very clear distinction between where the service layer runs, that is the VPN, and then where the transport layer, basically the LSP. We'll talk about LSP in a few, where LSP also runs. So when it comes to troubleshooting, you're able to know that this issue lies in the VPN, and this here I'm talking about VRF, and all this particular issue lies within the label switched path. That's what LSP means. Now, what we can do is go and tackle number 10, then quickly be able to answer the question that Elisa had asked, when MPLS is not necessary. So operational advantages here is that this is again for those who are working in a service provider environment, which I'm lucky to. So MPLS will give you predictable path behavior because, well, as you saw earlier, one of the benefits, number 1, was traffic engineering. We've been able to already establish paths. We've reserved resources, and so therefore we know we know how a particular path behaves if you do add more customers to it or remove more customers to it. Now, you also have the ability to isolate faults per VRF. So whenever we have an issue within your MPLS code, it doesn't really mean that it's a global thing. So what MPLS offers you is that it gives you the ability to isolate those faults per VRF. Customers come into your network, they are assigned a particular VRF just to distinguish them from each other. Now, lastly, we've talked about MPLS and its benefits. So there are scenarios where you don't really require to run MPLS. And number one is when you have a small network, and then if you only need basic routing, then you don't need MPLS, because you'll just have to do the basic routing and save yourself from the trouble of having to configure MPLS within your network, which, by the way, is a very simple thing to do. Configuring MPLS is very simple. In fact, much of the work is be able to configure IGP and make sure that within your MPLS network, you're able to learn routes of the core routers. Therefore, it's not really saving your time or saving the trouble of configuring MPLS, but you don't really need it when you have a very small network. And nowadays, if you talk to Martin Madiba and the others, they will tell you that SD-WAN, this is what is being spoken to about a lot these days. So a lot of companies, because SD-WAN is a newer technology compared to MPLS, you'll find that some companies actually leaning towards software-defined wide area networks. So that you will not actually require to run MPLS when you're running SD-WAN. However, MPLS is still being used in service provider network, and just like we have IPv4 and IPv6. We've been hearing about IPv6 for a very long time, but we still have IPv4. So in my opinion, we're still going to have MPLS for the foreseeable future. Therefore, that's why it's important for us to learn and be able to know how MPLS works. Okay. Let's move. So let's do a summary here. So life without MPLS and life with MPLS. Now, in terms of differences when it comes to how the path is selected, when you're not running MPLS within your network, IGP basically decides the path, either ISIS or SPF. The shortest path wins, irrespective of bandwidth constraint, irrespective of whether that link is degraded or not. If it's the shortest path, then it will be selected. With MPLS, you're able to control that. The moment you realize that this particular, not even the moment, there's a way you configure MPLS, especially for traffic engineering, such that when a particular path is degraded or a particular path does not have enough capacity or bandwidth, then another path should be chosen automatically. Okay, so for so for network without MPLS, all the core routers are able to see all the routes, all the customer routes. In this case, I'm talking about the customer routes. Whereas in MPLS, the core is clean. And when you're talking about the core, I'm talking about, let me use a different color here. When I'm talking about the core, I'm talking about these particular devices here. I'm talking about this. I'm talking about this one here. I'm talking about here and this one here. I'll be able to show you shortly what those ones mean within the MPLS background or the service provider perspective. So these routes here are unaware of customer routes. For example, this customer here, its routes are not known to these particular core routers. The only device that knows about these routes is the PE device here. The PE device there, this device here, and this device here. These are the only devices that know about the customer routes. The rest do not know about the customer routes. And therefore, it makes it, if I can use the word, less congested when it comes to having a very large routing table. So that only happens here and here. This core here does not have any information about the customer routes. Okay. Then let me clear this. When it comes to segmentation, of course, we have limited segmentation when it comes to MPLS. But without MPLS, but when you are employing MPLS or deploying MPLS, then you have massive VPN scale. As I said, you can have 1,000 customers. You can have 1,000 customers connected within your service provider network, and all those customers are actually able to use overlapping IP addresses without problems. The same thing cannot be achieved actually when you're using normal IP routing, because if this customer is if you're using the 10.10.0.0.0/8 network for about even, let me say, even 5 customers. Now, for you to be able to ensure that these customers, the 5 of them using this particular prefix, are isolated from each other, it's a very huge task. Of course, there's some configuration that you have to make to achieve that, but it's tedious, and why use that and when we have MPLS? Yeah. So that is that. Now, MPLS is, of course, rerouting. We spoke about slower convergence when we don't have MPLS, and we have very fast convergence or reroute whenever there's a break within the primary path. Therefore, traffic is being rerouted to the working, now healthy path. So MPLS is used to provide scalable traffic engineering, service isolation, that is L2 VPN or L3 VPN. Then there's fast forwarding and predictable end-to-end transport across a provider backbone without exposing customer routing information to the core network. Okay. I've been talking for a very long time. Questions, please. 1 or 2 before we go on.
Yes, David, we have some questions on the chat. If you can
Okay.
open the chat. Those one are already posted there, so we can start with them.
All right. Let me go there. What does the chat? What the guys say in the chat? Is there any Olayemi says, oh, this is the first one. Oh.
Yes.
Yeah. Olayemi says, is there any QoS marking for signaling? Martin, you understand this question? Is there any
Of course, there
QoS
are
marking?
QoS marking, but when he mentions about signaling, I don't know which kind of signaling he's talking about.
Yeah. But of course, in MPL, sorry.
Yes, just proceed, David.
Yeah, so when you talk about QoS marking, of course, in MPLS, the MPLS header itself being a 32-bit, it has been broken down into four categories where you can have the XP bits, which basically is a traffic class. And this is where QoS markings are done actually. I'm not sure about the part of signaling, what it means. And then the same, Martin?
Yeah. Can you guys hear me?
Yeah.
Yeah. So I think what the gentleman is trying to ask is broader. So cross signaling, it will be if you want to do voice signaling, etc. So what can be done there? So in the presence of the PE, you can match the customer traffic based on maybe source and destination, or the SIPs or the SIP signaling ports. And then once that happens, and then you assign it with the MPLS experimental topmost label. And then with that experimental topmost label, when it's sent to the core has a list of labels where it's instructed to focus on. If it's coming from XP5, prioritize it. If it's coming from XP3, prioritize it. So I understand. I hope that answers the question.
Yeah, I think that maybe that's what Olayemi meant. That is basically what those particular 8 bits are there for. Martin, you put it very, very well. He also asks the difference between IP fast readout and IPM fast readout.
Sorry, let me just buttress on the question. I mean, so I know I've come across QoS marking that has to do with CS7, CS6, I think AF4, AF2, best effort,
Yeah.
and all that, whereby I think CS7 is basically meant for signaling, while CS6 is used for routing. Then maybe you can place voice traffic to AF4 and maybe data traffic to AF4. I can't. Okay, EF. There is EF. So I think my question is along that part. I don't know. I think there's something like that in Huawei.
So there's something
Like this marking of different traffic, maybe in a mobile service environment. I mean, a telecom service provider, whereby you categorize or you mark traffic in respect with this marking like CS7, CS6, AF4, AF2, EF, and all that. The CS7 basically for signaling, anything signaling that has to do with probably the first of all establishing the signaling section. Then CS7, I can't remember, maybe there was CS7 for routing, CS6 for signaling. Then you can place the data traffic on AF4. EF is for voice, and maybe other enterprise services can be best efforts and all that.
So you're asking if MPLS is able to offer you that?
Yes.
Yeah. I mentioned about that Olayemi when I was talking about the experimental bit which Martin Modiba has actually explained. I'm not sure if you followed him very well. Yes, Martin.
Yes. So let me rephrase. So what happens is in the MPLS experimental topmost label table, it makes reference to the IP precedence table from 0 to 7. So whether it's Cisco or whether it's Huawei, so CS6 and CS6 and CS7. So what happens is those two. So number 7 will be for network management, and then for CS6 will be signaling for your CAPWeb, for example. If let's say you are using maybe let's say tunneling, for example, that traffic will also be marked by default under the CS6. So then what will happen is some applications by default, they do come with their default markings, whereby in quality of service, you can have an option of marking or matching the actual marking that's coming from the application. Some applications don't come with it. That's where now you need to match the specific traffic and then give it that respective marking. But to answer the question, it's highly recommended that you don't touch 6 and 7 because they are reserved for the network.
Yeah. Olaemi, I hope you're good with that answer.
Yes, thank you.
Perfect. Elisa, please make it quick so we can move, please. Elisa, what's your question?
Yes, Brother David. My question is first, I always want to know why and when to use something. You know. So you said that, of course, when you have too many entries, too many routes in your network, when you have a big network, then you have to use MPLS. But is that the main reason can someone sit with other people around on the table and decide like, okay, for now, we have to use MPLS because of this and that. The main thing that can push any company to implement MPLS on their network.
Okay. So so Elisa, just to answer your question, there is no one single reason as to why you should use. I should advise someone to use a MPLS or not. I've been able to give you about 10 advantages of MPLS. You know what it offers and what IP routing also has to offer. So when it comes to you deciding when or if to use or not to use MPLS, again, this will go back to what are the requirements? What do you want to achieve? What are the network requirements, or what does your customer want? So from there, that particular, if you answer the question, what does the customer want, or what do you want to achieve within your network, then you'll be able to decide if you're going with MPLS or not going with MPLS. But if you're looking for one specific answer, then I'm afraid I would not be able to tell you that's specific, because all of us here come from different backgrounds, different work background, that is. So what you do within your enterprise, what I do within my enterprise or service provider network is totally different. Therefore, the choice of MPLS or not comes down to your customer requirements or your network requirements.
Okay. Thank you.
Ali, hope that's the last question so we can move. We have about 30 or so minutes to complete.
Thank you for allowing me to ask and attend your meeting. I would like to thank David for his demonstration in this video. The way he speaks is phenomenal. Thank you very much. I would like to add one thing to all my fellow listeners. Just trying to add a point to David. Not my intention to add more to his word, but to try to explain it in my view. Using MPLS, I think it gives you a very like if you're a mechanic and then you have tools. The more you have tools, the more cars you can fix. So MPLS adds a set of tools that you can't have in any other protocols, and then hence when you have more tools, you can be able to fabricate things and do things that other shops can't do. I hope that makes sense for everyone. So my question is, I understand your explanation, and it's terrific. But I would like you to emphasize the network design prospect, because since MPLS is an overlay on the already running IGB protocol that hinders its applicability when you're not running a consolidated design in the first place. So if you have a bad network and then you're running MPLS on top of it, you're adding complexity to already complex situation, which is gonna be a bad experience for everyone. And I'm not saying this to I'm asking you to show me. I don't know. I know this fact, but I don't know how to. I don't fully understand it.
Okay. Okay, Ali. Hopefully before the end of the session, I'll be able to. I have a slide on that. I'll be able to show you how to design that, especially when you're talking about L3 VPNs. I'll be able to cover that. And thank you for that analogy about being a mechanic, and we have more tools, the more cars you can fix. So thank you so much for that addition. Let me answer the last question so that we can proceed. Olayemi asks what's the difference between IP fast reroute and VPN fast reroute. Now, we don't really have the term fast reroute when it comes to normal traditional IP, at least the best of my knowledge. But what you use BFD. That's by the BFD. Bi-directional forwarding. So you can use BFD with either OSPF, ISIS, or even static routing, even BGP. So that will be you'll be able to set the parameters that you need so that you can be able to achieve fast reroute when you're just doing normal IP routing. When it comes to VPN, and this is where MPLS comes in, you actually have the keyword fast reroute, and then you have to configure the backup path, which by default it gives you less than 50 millisecond switchover. That's convergence. So that's the difference. The difference is based on what configurations or what mechanism you're using when it comes to a fast reroute. And then Obina, yes, these slides will be shared. Martin will be able to share the slides with you. What lab resources softwares are you using? I'm using EvenG for the lab. I think you've seen I'm using a PowerPoint. Yes, can we get the same? The slides will be shared. Yeah, thanks, Martin, for answering. Which channel? Okay, Martin, I think all the questions are done. Eh? We can proceed.
Yes, let's proceed
Yeah,
with the remaining slides.
let's proceed so
we can take a few more questions at the end.
Yeah, thank you. So with common applications for MPLS, Elisa will find this one in service provider wide area networks. If you're running an ISP, which is a large ISP, for example, then you'll be able to use MPLS. It will serve you very well. Enterprise ones also, if like the analogy that I showed you, that where the company this particular customer here is wants to communicate, is in Uganda, wants to communicate to a branch in, for example, France. You're able to achieve that with MPLS. Sorry. And then we have, of course, the L2 VPN and the L3 VPN. These ones here, we'll have to talk more about them when we're doing the lab. Everything will come, will be very clear when you're doing the lab. We'll be able to do one lab that has L2 VPN and L3 VPN combined. And then traffic, of course, we've spoken about traffic engineering and what that gives you. And of course, nowadays in mobile backhauls, you're able to use MPLS. Martin, can you confirm that you use MPLS?
Yes, we do.
Thank you. So now, there is no good thing that doesn't have a downside. That's the reality of how things are. So you cannot be perfect. You have your shortcomings. So as good as MPLS is, it also has the disadvantage side of it. It has very many advantages. Yes, we both agree. If you've been very fortunate enough to work in an environment where MPLS is deployed, then you know what the benefits are. But at the same time, we have the disadvantages. And here I've just sampled about 4. Now it's complex. For you to be able to, like Ali has said, if you run MPLS is kind of a overlay. It doesn't work on its own. You have to configure, like I said, an IGP, either ISIS or SPF. Then you be able to leverage. And luckily for us, ISIS and OSPF have extensions for them to be able to work with MPLS. Now, the complexity part of it is that you require advanced knowledge of network knowledge. That is, you require advanced networking knowledge for you to be able to effectively run a complete MPLS network. By complete, I mean a network that has MPLS traffic engineering, QoS, the quality of service, and all those components. You need to have a very good knowledge about it, because if you do not, then it will bring chaos to your network, and then you not be able to achieve the intended purpose. Another disadvantage of MPLS lies on the cost, and mainly this is a cost that is incurred by the service provider. All right. Now, if I can briefly go back to my topology and show you something. So, assuming this is your network, your service provider network. Now, I've been able to name these devices with names so that you can be able to understand this concept. So, for you for these customers, for this customer in Uganda, for example, this customer in Uganda, and then they have another branch in France. Okay, I said FR means France, FR means France, and then UG means Uganda. So imagine, for us to be able to provide services to these two customers, it means we need to have presence in all these countries. We need to have a network that runs all the way from Uganda to France. If we do not have that network, then we can leverage the use of another service provider. But that again, that's a topic for another day. But assuming that you are the ones that you're the one that has this particular network, then building this infrastructure itself, it costs. It needs a lot of money, to be honest. Right from permits within the relevant countries, and then you have equipment, laying down the infrastructure. So it's costly in a nutshell. So and you'll find that since it's costly to the service provider themselves, they may actually trickle down this particular cost to the end user, the end user, who in this case is the customer. So that cost, they have a way of making their calculations and ensuring that the customer also has to pay a lot of fairly large amount of money for them to be able to get that particular service. And remember, one of the advantages that MPLS offers is security, as opposed to just the traditional IP routing, where MPLS service providers will give you more security. That's why they'll make sure that your routes do not, in one way or the other, leak into the customer, meaning customer A does not see customer B's routes and vice versa. Now, we have another disadvantage whereby enterprise networks or small ISPs or small networks will rely heavily on the service provider network, because this customer here, again, does not have an infrastructure of their own from Uganda to France. So what they do is they have to rely on the service provider network. And therefore, in so doing, it means that they'll have to pay a fee for them to be able to use this infrastructure here, the one that is in dotted line. They have to pay that fee to use this infrastructure for them to be able to use their services to reach the customers at this end. Therefore, this again goes back to the issue of cost. To be able to leverage the use of the service provider or the carrier, That's a disadvantage because you have no control of this thing. So assuming there's an outage, for example, you have to depend on the service provider for them to be able to sort that outage, and then your services are a backup. So that's a disadvantage because as a customer, the end user customer, you do not have control of what happens within the service provider in terms of outages or even upgrades and something like that. Because if I have a maintenance as a service provider, I'll have to of course notify you that I have a maintenance, and that again is something that these customers here do not have control over. Let's quickly run. So AD1, SD1, we spoke about SD1. A lot of companies are now moving towards software-defined wide area networks and not really abandoning, but not using MPLS anymore. Of course, to the best of my knowledge, SD1 is a bit affordable when it comes to cost, and even how it's deployed compared to MPLS. So those are the disadvantages of MPLS that I could come in. Now, let's talk about MPLS architecture. We've talked about MPLS, what it is, advantages, disadvantages. Now, architecture. So let's put this into a paper, for example, and so that you can have a visual of how this works. Now, within the MPLS architecture, we have devices, and those devices have different roles in an MPLS network. They have very specific names. They have very specific roles that they do, and therefore, for you to be able, and then I think this will answer Ali's question. For you to be able to deploy or effectively deploy and manage an MPLS network, then you need to know these particular devices, what they are, and their roles. And they're luckily for us, they're not many. So when it comes to the perspective of the service provider network itself, we have three devices. Number one, we have the P devices. And basically, these are what we call the provider routers. These are the core routers. These routers are not normally. These routers will always be found within the service provider network, and they connect to other provider routers and provider edge routers. For example, this is a P network. This is a P router. This is a P router. This is a P router. This is a P router, provider edge router. And as you can see, they only connect to other P routers and PE routers. They do not connect to customer edge routers. Okay. And another thing about provider edge networks, you do not run any kind of BGP within these devices. That's why in some literature, they will call this BGP free core, which means the core routers here, for our case, we have 4. These core routers here, they do not run BGP. They do not connect to customer devices. They only connect to other provider routers and provider edge routers. That's it. And we'll get to see what their roles their role is within the MPLS network. Number 2, we have the provider edge, PE. Now, these one here are at the edge of the service provider network. At the edge, figuratively, like technically speaking, as you can see here, the topology that I'm using here, you can see this is the PE router. This is another PE router. As you can see, inside this box, this is the provider. This is the service provider network. Now, this provider edge routers, as you can see, they are at the edge. They are at the edge of the provider network. Now, these provider edge devices connect to PE devices, and they can also connect to other PE devices, depending on how you could have another PE device here actually, and it can connect to each other, and they also connect to CE or customer edge router. Okay. Now, this PE router, their sole purpose is actually to connect the customer edge routers or device to the service provider network. Now, this is where PE and CE routing takes place, like that. And for the case of L2 or for the case of L3 VPN, the CE to PE routing here, you can use any IGP. You can also use BGP, as we'll see during our lab. But basically, that is what the PE devices or the PE routers do. They connect to the customer. They can connect to they can connect to other PE devices, and they connect to PE devices. Now, another thing is for this customer routes here, assuming this customer has routes, and then they want to communicate with this customer here. So this is they belong to the same company. Now, and then down here, this other one here and this other one here belong to the same company. Okay. Now, if I want to transport, basically or literally, if you want to transport the routes for this customer to this customer, what will enable me to do that within L3 VPN context again is I'll have to configure MPBGP, specifically IBGP, MPIBGP between this CE device here and this this PE device here and this PE device here. Now, this is the only place that BGP and specifically MP multi-protocol IBGP is configured within the service provider network. Other devices do not have to be configured. Actually, they're not even aware of BGP. So that is for PE device. Now, within the context of MPLS now, the PE device has another name called label switch router or LSR. And then the PE device has a name called label edge router. Okay. Now, this can either be ingress or egress, depending on where the traffic is flowing. If traffic is flowing from this customer to this customer, then this PE here becomes an ingress label edge router. If traffic is flowing from this device to this device, then this PE here becomes an ingress label edge router. So if this is ingress, then of course now this one becomes egress, and vice versa. So those are the device roles that we have within the MPLS architecture, and it's important for you to know those roles and understand them and know what each device does within the MPLS architecture. Now, this is something we'll come back and talk about. Let me talk about the provider edge router now. So what is the role? As we said, it connects directly to customer networks. It acts as the entry and exit point of the MPLS network for customer traffic. Now, this is where labels are pushed. So I think I'm gonna grab this photo here. I think I'm gonna grab this one and do something for you guys. Oh, sorry. Just bear with me, because now this is important and I'll have to use it. Nice, got it. Okay. So let's go back to our slide. So this is where labels are being pushed. So if we are coming from this direction, so label will be pushed. It will come to this router. It will be swapped. It will go here. It will be swapped, and then this one here will perform what we call PHP, as we'll be looking in a few. That is penultimate hop popping, And then finally, that particular packet arrives at the egress label edge router before it goes to the customer. Okay. We go back and do so, and then so the PE router is responsible for maintaining customer routing tables. So if you have this PE router here, that is a UG PE router, and then this customer here is given a name Amani, say 10. So if you log into this PE router here, for example, so this PE router has a global IP, it has a global IP table, routing table, as you can see. The customer routes here, that is Amani. As I said, this is a theory, but with a practical approach. If we go, let me clear this a bit. If you go and say show IP, if you go and say show IP route, these are all the routes that are found within this customer here, this customer CE. As you can see, we have 192.168, and then 192, that this is .0.100.0, and then we have 10.10, and then 13. If you go to UG, when you look at the global routing table, there are no those customer routes are not here. If you're able to scan quickly, those customer routes are not here. Okay, but if you go to display IP routing, VPN instance, I think that's some money. If you go to this specific routing table, and it clearly says here, this is routing table for Amani. You're able to see those particular routes. So that brings us to the point that it maintains customer routing tables per VRF. So if we had another VRF configured, another customer configured to this particular PE device, will be able to have its routing table as well. Now, it runs MPBGP, specifically IBGP. Also, when it comes to PE to CE peering, you could use either OSPF or ISIS. That is one that I would recommend. But the best for this particular lab and that I'm using for this demonstration and the next one, I would prefer to use BGP as the BGP as the PE to CE peering, because it's actually very easy. Because if you use OSPF and ISIS, then it will mean that you will have to do route distribution within this particular device, which could also be a bit complex and time consuming. Okay. So in terms of what it does, it pushes labels stack. That's the ingress PE. The egress one, it removes or pops the labels before it forwards the packet to the CE. And then it assigns and uses VPN labels. Now, the provider edge device, okay, understands customer routes. That is the only device that should understand customer routes. Other devices, the PE devices within here, do not even know there's a customer called Amani that exists in this particular network. That is the work of the PE device, and as you can see, it's a very special kind of device. So please, I'll be sharing. I will not be going through, in the interest of time, I will not be going through all the literature here, but I'll share these slides for you to be able to go through and understand what each device does. Number two, we have the provider edge, which is basically the core router. Where it's located, it's within this the backbone of the MPLS network core. Again, as you can see clearly here, and then it does not maintain any VRFs, and it runs IGP only. Okay, no BGP, just IGP, either OSPF or ISIS. And these two are the preferred one, because as I mentioned, they have been designed, they have extensions that enable them to work well with MPLS. They maintain VRFs, and then they do not run any multi-protocol BGP. they do the label swap, or at some point they can do the penultimate hop popping. For example, if this label here, if this service, if this packet comes to this PE, it is a label is imposed, and then it pushed to this PE, it is swapped with another label, it's taken to this other PE. Now this PE, because this is the last PE before it goes to the provider edge device, now this is where PHP is done. Penultimate hop popping, second to last. So basically it removes the label before it forwards the packet towards the PE device. And then when it goes here, it has no label. Let me show you that. Let me show that in action. So assuming that we are here CE10, this device here, and we want to ping, or sorry, we want to trace Amani, say 13 in France. We're in Uganda, we want to go to France. So what you can do is the loopback interface of this device here is 13, 13, 13, 13. So I want to trace that. As you can see, it's within our routing table. So if you trace that and say trace, I think this is Cisco. Yeah, this is Cisco. Trace route 13, 13, 13, 13. As you can see, now let's follow the path. We first of all go to our gateway, which is .1 here, which is this device. And then from there, we go all the way to, we use this route here. We go to this device. Now, I want to take note of this label here, and this label, and this label. Did I do something wrong? So this label here, this label, and this label here. It is constant. It doesn't change. Now, it goes to 3, and then from there, it goes to 2. This device, it goes to 4, and then finally it arrives at 104. From 4, of course, it comes to France. As you can see, the last hop. The last octet here should be telling you the device name, so the device number. For example, this is 6, then therefore this is France P6. Now, when it comes to L3 VPN, when you configure multi-protocol IBGP between this guy here and this guy, once you've configured a protocol IBGP, remember this device here can reach this device because we've configured ISIS. Therefore, there is connectivity within the MPLS core. And since we have connectivity within the MPLS core and the loopback addresses, IP addresses of these devices here are advertised in ISIS, meaning the Uganda PE can learn routes within this MPLS core, including the loopback address of this particular device. Therefore, we come up with multi-protocol BGP. Now, that multi-protocol BGP is of VPN v4 type. We're not running IPv6 here, so we're doing VPN v4. So what that does is, it's after we've configured multi-protocol IBGP in this device here, and then we have PE-CE pairing. So this device learns routes from Amani CE10 and then stores it in the IP in the routing table of Amani. That's the VRF. Now, those particular VRFs, because we employ the use of what we call route targets, and route distinguishers. Again, that will be covered in a few. What that does is those routes are able to be carried all the way to this other device. Now, this device, for it to be able to reach this particular PE device here, okay, it has reachability. It has all these routes within its global routing table. So it knows that for me, this particular PE here, this particular PE, let me clear this. this particular PE knows that for me to be able to access this network, I'll have to go through P06. Now, P06 says, yes, that's fine, but for you to access P06, you must have a routing table. You must have reachability to me, and therefore, when you go to Uganda PE, and I'm explaining this because I won't be doing it again because it will form the basis of our discussion. So if you go to this PE, the loopback IP address of this particular France PE is here. So we've learned it via ISIS, and I can ping it. There you go. So we can ping it. Now, so this France PE 06 tells Uganda PE 01 that if you want to reach this particular network that is connected to me, then you have to go through me. Now, this guy asks, how do I go? How do I reach? How do I know where to go or what to use to reach you? Now that's where you have to be able to configure MPLS within the service provider core. Once you configure MPLS there, labels are able to be assigned to specific, not all the routes. If you remember, you talked about the FEC, forward equivalent class. So inside the display, if you display MPLS LSP, this is how you display the MPLS forwarding table in Huawei. The command is display MPLS LSP. So we are able to know that we need to, if you have to go to 6, then you have to go through 2, or we can go, you have to go through this particular node all the way to 6. But what I want to show you, which is interesting, is how this label here, how this came into existence. This label was assigned by this particular device, showing MPLS forwarding. As you can see, that is your label. Where was I? 616. France 616. There you go. So this device tells Uganda PE that for you to be able to reach, this is the label that I'm giving you. Now, this label here does not change because, like if you remember, we have the label stack, 2 labels. We have the transport label and the VPN label. So basically, this is the VPN label, and it does not change throughout. It only gets after it gets it does not change because it is used by the egress PE to be able to identify where to forward that traffic to. That's why it does not change. But these other ones here, the transport labels change based on what P devices they go through. Now, I'm not sure if I've lost anyone, but let's go back to the slide and talk more. So that's what happens within the provider device. Now, a key important thing to note here, which I've emphasized here, is the P device that they do not know anything about labels. The VPN routes. They only know about, for me to go to this particular one, I've been instructed to use this particular label. That's it. So when it comes to customer edge, the role, again, where the customer edge device is located, of course, it's located on the customer side, and then it connects to the PE device. Now, the customer device runs standard IP routing. There is no MPLS. There is no MPLS for the customer, for the CE. These devices here do not run MPLS. There's no MPLS here, no MPLS here, no MPLS here. Meaning this interface, there's no MPLS, there's no MPLS, no MPLS, and also here, no MPLS. Okay? And then here, you for standard IP routing, you can use static routing, you can use SPF, ISIS, or RIP, or BGP. There is no MPLS. It does not have any label responsibility, no MPLS label at all now. The summary of that is that the customer-facing device does not have any knowledge of MPLS. So those are the device roles, and we'll be able to. So this is I won't going to go through this. This is something you can go through yourself and understand how traffic flows from using this device here, from CE1 all the way to PE1 to the two PEs, and then goes to the provider edge 2, finally goes to the CE2. And this is what happens at every stage. Okay, this is what happens at every stage. Now we've talked about L3 VPN, but now let's talk about it in a bit in more details and understand what it means. So what is a VRF in L3 VPN? Basically, VRF stands for virtual routing and forwarding. It means within a physical device, for example, this PE here, you are able to come up with multiple routing tables for different customers. If you have, so there's a global routing table, and then there's the VRF. So this VRF routing table, you can have as many as your PC capabilities can support. So the VRFs basically are able to segregate, or they're able to, for lack of a better word, they're able to hide other customer routes from, they're able to hide customer routes from linking into each other. Now, so this is the component that enables customer traffic separation and routing isolation on the provider edge. We only configure VRFs on the provider edge. We don't configure VRF on CE or P. Now, each VRF has its own routing table. It has its own interfaces. It has its own forwarding decisions. Now, this allows multiple customers to be able to use the same IP address space. They are able to share the same MPLS backbone or service provider network, and they remain logically isolated. But if you want, for some reasons, the customers to be able to communicate to each other, you can configure out leaking. Depending if, for example, the customers want to merge, therefore you can configure out leaking for them to be able to see each other's routes. Okay, so what we need, what we need VRF for is, already we've spoken about it, is that imagine if we didn't have separate or different routing tables for different customers, all customers would mix in the global routing table, and this will bring about conflict. So what VRFs do to us is that we are able to use overlapping IPs, and therefore, because we know IPv4 address is almost being exhausted, we're able to preserve IP addresses whenever we use VRF. There is no route leakage unless explicitly configured, like we've said before. All right, so the core components of L3 VPN. Now, for L3 VPN to be able to work, we are specifically concentrating on L3 VPN because it's the most common use or common application of MPLS. Now, there are about 4 components that you need for VRF, basically L3 VPN. What you need a route distinguisher, which is a 64-bit. So this route distinguisher, from the word distinguisher, is able to make routes globally unique within MP-BGP. It's globally unique. If you run a command, Cisco gives it in a very good way. If you run the command show BGP VPN v4 unicast, show BGP VPN v4 unicast all. This particular command should able to, if we had other VRFs here, so this tells you this route distinguisher is for VRF Amani. If we had another VRF, which will tell us for VRF ABC, for example. So it's the route distinguisher is what makes the routes globally unique within the MPLS, specifically multi-protocol IBGP. Now, for example, you could have the same customers using the same IP address range, but having the same different route distinguishers. What this does is that it ensures uniqueness it ensures uniqueness of those particular routes. So if customer A wants to communicate to customer A site 2, for example, they will be able to ping each other, no route leaking. Unless of course they want to merge, and then therefore you have to explicitly configure route leaking. Another component is the route target. Now this is what controls what you import or export. It controls what routes you have to export or what routes you need to import. Okay, so the export route target, it tags routes as they leave the VRF, and then the import one, it also selects which routes should enter that specific VRF. This is what actually makes the separation of, again, separation of customer routes possible. For us to not have the conflict of the customer routes, we need the route distinguisher, and then we need the route target. They work hand in hand. Now, after all that, after having the RD and RTs, now the third component is the VRF routing table, which of course keeps customer routes separate from different customer. And then it has its own routes. It can be connected routes, it can be static, it can be BGP. It works the same way the global routing table works. The only difference is that particular routing table is for a specific customer, or in this case, a specific VRF. Now, for L3 VPN to work, we have to assign interfaces to specific VRFs. For example, the interface, no, this is not, the interface here that connects to Amani CE, this Ethernet 103 in Huawei, you have to add this particular interface to a specific VRF. And remember, one interface can only be assigned to one VRF. You cannot have two VRFs being configured in the same interface. It will not work. And then you have to assign a VRF to an interface before you configure an IP address. If you do not do that, then the IP address will be removed. Then you have to reconfigure it again. Then you will, this one we'll see when we are doing the lab. All these things will be very clear when it comes to the lab. So how you do the VRF assignment in Cisco, basically this is the command. You first of all enter the interface. Then inside the interface, you can choose to have a description. I choose to have descriptions because they are able to tell me what interfaces I'm dealing with or what services those interfaces are offering. So you first of all enter the interface, and then for Cisco, you issue this command VRF forwarding, then you give it a name. Then the name in green is what I've decided to use to give this customer. So customer A, for example. Then you assign an IP address. In Huawei, NE40, but basically Huawei, the syntax is almost the same in all their flavors. You again enter the interface, that is 102 in this case, and then you issue, instead of VRF forwarding, in Huawei it's IP binding VPN instance, then you give this name, and then you issue the IP address. This is how you configure or how you assign VRFs to CE facing interfaces. Remember, VRFs are only supposed to be assigned to CE facing interfaces, meaning you assign VRFs here, here, and here, and here. Don't assign VRFs here because that will not work. That will not work. Okay, we are almost done. We are almost done. Now, we've briefly discussed about MPLS, L2 VPNs and L3 VPNs, the theory part of it, and I'm skipping a lot of theory because I would want us to discuss this thing when we are doing the lab, because it will become very easy. But in a nutshell, the difference between L2 VPN and L3 VPN can be summarized into these 5 features. Number 1, where they lie within the OSI model. L3 VPN, of course, from the word L2, is it lies in layer 2. For L3 VPN, L3. When it comes to what is carried, L2 VPN carries Ethernet frames, then L3 VPN carries IP packets. sorry, let me take that again. L2 VPNs carry Ethernet frames. L3 VPN, they do carry IP packets. When it comes to who is responsible for routing, so for L2 VPN, routing is actually done within the customer device, the CE device. Whereas in L3 VPN, routing is done at both ends. You configure at the customer the customer's end, and also you configure at the provider edge device. That's where routing is done, and you can use any routing you want to use depending on the environment you're working on. If it's a multi-vendor environment, then I would advise use either OSPF or ISIS. But for simplicity, you could also run normal IBGP, so normal eBGP between CE and PE, meaning between this interface here you could run BGP, you could run ISIS, you could run OSPF. But the reason as to why I'm championing for BGP, eBGP in this case, eBGP. The reason as to why I'm championing for eBGP is because you not have to do route distribution within the provider edge device. But when you're doing ISIS and OSPF, then you definitely have to do route distribution. And this is something that we will be able to achieve in the lab. Customer view, it simply means that the customer, when you're doing L2 VPN, L2 VPN, so what happens is the service provider network, for example, let me just scribble something here. When you're doing L2 VPN, the service provider network, so this is the CE, and then this is another CE. So this is the service provider network. When you're doing L2 VPNs, this service provider network becomes like a very big switch. So therefore, these customers here act as if they are connected within using a switch, and therefore offers point-to-point. So when it comes to how it appears to the customer, it appears as a direct layer 2 link. But for L3 VPN, it's a routed wide area network, because you have to do PE to C, you have to do PE to C peering, and then therefore do multi-protocol IBGP for you to be able to propagate all those routes from this customer here to this customer here. So basically that's what it means. And then lastly, we have the MPLS role here is that it just becomes a tunnel, like I said, a big switch. But for L3 VPN, we have those tunnels configured, and then the service provider network and the customer participate in routing. Those are the major differences between L3 VPN and L2 VPN. And again, in terms of which one to use, which one not to use, well, it depends on what the customer requirements are. If the customer comes and says, for example, in our example here that we'll be able to use next time, this customer here comes and says, I want IPT services, meaning I want to peer. You have some peering in France. This is Google. This is Facebook, and so I want just to get this content here. So since this customer is in Uganda and doesn't have the infrastructure on their own, so they leverage the use of our service provider network. So what we do is we configure L2 VPN for this customer, and then be able to configure BGP. This is what we will be doing in our lab, but just let me give you what happens. You configure BGP between this device and this device, but it has to go through the MPLS core for that to work. It has to go through that, and this will be explained in a later session. For now, we're just focusing on the theory part of it. So we have come to what we call the MPLS label operations. Basically, there are three of them. We either push labels, that is imposition of labels, we either swap them, or pop. So pushing is basically adding one or more labels to a packet. Then where it happens at the ingress PE. Okay, or sometimes it can happen in midpoints like in tunnels, but this is on very rare occasions. The normal behavior is that pushing when the packet arrives at this PE, before it goes to this PE device, a label is pushed, and that label is a transport label. When it comes, say it's swapped, the VPN label remains. Remember from the trace route we did, it doesn't change. Then it comes, say it's swapped or popped, but it's forwarded with it with the VPN label. Now the transport label is popped, doesn't appear before it goes out as a normal IP packet. Number two, we have swapping. We've already discussed about what swapping is. It replaces the top label, which is a transport label, with another label. It's performed by PE routers, and sometimes this swapping can also be done by the PE routers. Okay. Now, only the top label is changed. The inner labels, which is the VPN label, remain untouched. Now, the reason as to why the inner label remains untouched is because it's the one that will be used by the egress PE to be able to know which VRF table those particular customer routes are supposed to be added to. Number three, we have popping, which is basically the last one. We have popping, which is label removal. You strip the top label, which is the transport label, and remove remove it from the packet, but you leave the VPN label. As you can see, the trace that we did here, we were able to swap all the way. We were able to swap all the way to here. But when it got to the France PE, let me just go back there quickly. When it goes to the France PE, what happens is the transport labels were removed, but the VPN label was retained. This is the label that is now being used to know that this particular request is supposed to go to this customer, which is down here. So popping, you only pop the top label, which is the transport label, but the VPN label remains. The VPN label is only stripped by the PE device before the IP packet can be forwarded without any labels to the destination. Okay, I can see still have people logged in. So thank you so much for staying with us until this time. We're almost done. Now we have two types of popping, and these are very interesting terms that I like playing around with when I'm having a discussion about MPLS. So we have penultimate hop popping, which already we discussed about it. This means second to last, and ultimate pop, which means this is done by the PE device. This is done by the PE device. Now, penultimate hop popping simply means that the transport label is removed. After it's removed, what goes to the PE device is a VPN label. Okay, so the importance of having the PHP operation is it reduces the workload on the egress PE, and then therefore improves forwarding instead of the PE again, because already the PE has the global routing, it has the VRFs, it has a lot that is going on. Then again, instead of tasking it with removing all those labels, so the transport label is removed by the PE device, and then and then now that particular packet is forwarded to the provider edge device with the VPN label intact, which allows it to know which VRF that particular IP address belongs to, and therefore performs the operation, and reachability between the two customers in Uganda, one in Uganda and one in France for our case, are able to communicate to each other. Now, ultimate popping is where all the labels, now, which means the VPN label which is remaining is removed, and then that IP packet, after the removal of that VPN label, the IP packet is forwarded in the VRF. This is where the VPN label is able to be mapped to a VRF, and then the packet is finally forwarded to the CE. So again, I've given a very short explanation of how L3 VPN works, end-to-end behavior. You can see our packet arrives from the CE1, goes to PE1, goes to PE, the first P, and then the second one. Then PHP is done here. then that particular packet is forwarded to the label edge router, which is the egress router. With the VPN intact, VPN label intact, the transport label has already been stripped off here by the PHP operation. Then from here, the label arrives here with the VPN label. That label is used to map it to the specific VRF before that packet is forwarded to the CE as a normal IP packet without label. And all that explanation is done down here for your reference. Now, lastly, we have to talk about, not second last, let's talk about the MPLS control protocols, what protocols actually run within the MPLS. So number one, we have routing protocols. Basically, you can use ISIS or OSPF within the MPLS core, meaning within here, all the interfaces that are facing your service provider network, sorry, that one is wrong. All these interfaces here that are here, you should be able to run an IGP for reachability, including the loopback interfaces. And then you can run BGP. BGP, as we said, the type here is MPIBGP. I should include that here. MPIBGP, which basically is the one that is responsible for route transportation. VPN v4, either if you're running IPv4, then it's VPN v4. If you're running IPv6, then it's VPN v6. So MPIBGP is responsible for the transportation of routes, customer routes from PE device to the other PE device and vice versa. And then the second control protocol that runs here is the label distribution protocols. Of course, you can use LDP. You can use resource reservation protocol, and then you have multi protocol BGP specifically unified MPLS, or some other literature will call it, I hope I'm getting it right, seamless MPLS. This is a topic on its own. We're not going to touch or discuss about it, but just know these are the most common ones that you'll find. Without traffic engineering, it's MPLS, it's LDP. But when traffic engineering is involved, then you have to use RSVP. And we're going to see about traffic engineering in a very short while. Lastly, not lastly again, we have the control plane and data plane. Just like the normal IP routing, even MPLS has the control plane and data plane. Basically, these particular planes, they work together for you to be able to achieve your network requirement. Now, the control plane generates and maintains routing information and label information. It runs IP routing protocols, e.g. LDP, and stores a routing information base and a label information base. So what you call RIB in the normal IP routing is lib in MPLS. What you call FIB, which is forwarding information base in normal IP routing, is called label forwarding information base in MPLS. I'm rushing because of time. MPLS control plane, this is what it does. It is responsible for learning routes, building forwarding tables, creating label mappings, and then distributing those labels. And it's established, it is used to establish label switched paths. This is the literature about routing information base and lib. And basically the protocols running in the control plane are, we've talked about ISIS, LDPs for distribution of labels, RSVPs for traffic engineering, and MPBGP, specifically IBGP again, is for VPN route exchange. All right, we are almost done. So the data plane determines how packets are forwarded. The same thing as what happens when you're doing normal IP routing. So we have the RIB, and then from the RIB is where the forwarding information base is gotten. Basically, the best route is entered there, and that is what is used to forward packets. The same thing here happens in MPLS. So data plane is responsible for how packets are forwarded in real time. And the label operations here are push, swap, and pop. We've already discussed about this. So this is a comparison between the FIB in normal IP routing and the LFib in data plane. Lastly, we have about 4 slides to finish. Lastly, Elisa, I'll come to you after. Just give me a second so that I can finish this. MPLS traffic engineering. Now, we gave this as one of the advantages of MPLS. And basically, MPLS traffic engineering is a technique that is used basically in large enterprises and service provider network to control how traffic flows through the network. Now, instead of relying the IGP, which you normally know, which we know uses the shortest path first, MPLS, we were able to have full control of how traffic is moving within this network of viewers. Because if it's IGP, let me use the purple color, it means this customer traffic might come this way here, and then it goes here, because simply put, this is the shortest path, or the other way around. But when it comes to MPLS traffic engineering, this path might be the shortest, but it is degraded, or it has high latency, or it doesn't have enough bandwidth. So what do? Then you have to configure a path, explicit path, that this traffic should come here. Then from there, it should come to this device. Then it should come all the way to this device before it finally goes to this provider edge device, before it goes to the respective customer. So that's what MPLS traffic engineering is able to give you. It offers you control. As a network engineer, you have to control how you're able to control how your traffic moves. And as we'll see, those operations are done at the head end or tail end. So if traffic is coming in here, this one here is the head end, and then this is the tail end. If traffic is coming from here, this becomes the head end, and then this becomes the tail end. Basically, that's what happens. Okay. Using MPLS to steer traffic over specific paths based on constraints, that is with bandwidth, path, and policy. So these are what actually this is what influences which path to use, rather than the default best path, which is in this case for AGP, the shortest path. MPLS can force traffic through specific paths instead of we've already spoken about that, so there's no need to repeat. So the key thing I wanted to talk about MPLS are these two here. To direct traffic along paths, MPLS TE establishes unidirectional tunnels called label switched paths. Now, for our case here, a label switched path can be this path, this path, this path, or it can be this path, this path, this path, or it could come to this, goes here, it comes here, comes here. That is a label switched path. Basically, that's what it means. So if you say LSP, it means this is a path that this particular this particular device will use to reach this device. So that path is what we're referring to as a label switched path. These tunnels are configured from the source to destination, that is the tail end, and are designed to meet specific criteria such as bandwidth, path, and policy. So we have bandwidth and other link attributes. Now, let's talk about what a label switched path is. First of all, we said it's unidirectional. Unidirectional means that path can be configured from here and say use this path. It does not necessarily mean that actually it shouldn't be the case. It doesn't mean that the return traffic should use the same path. Return traffic could use this other path. That is what unidirectional means. Okay, and for some reasons, if you configure an explicit path at this PE, which we are calling the head end, and say use this path to go to this PE and then exit out. And then you've not configured a return path on this PE. What will happen is traffic will come all the way you've traffic engineered it. It will go to CE2. So the return traffic, when it comes to PE, because there's no explicit LSP or tunnel that you've configured, what will happen is the PE will be able to use a predetermined LSP that has been selected based on IGP. Then it can just come, either use this route if that is the shortest route. Basically, that's what it works. So that's the meaning of the word unidirectional. It is not bidirectional, it's unidirectional. It's explicitly established to route traffic according to specific requirements, that's bandwidth and policy. It is a predetermined path that can deviate from IGP's shortest path. So it doesn't have to be the same as the IGP's established path. And then sometimes LSPs are referred to as tunnels. So how they are established, they use a protocol called Resource Reservation Protocol. This is a signaling protocol that communicates the constraints and the requirement of the LSP to all routers along the path. Now, during our lab, we'll be able to see how to configure RSVP on both Huawei and Cisco devices. So I strongly encourage you guys to also join that when it will be communicated. We're going to have fun in that particular lab session. So RSVP traffic engineering, now the best path of the LSP is designed using RSVP. We're no longer using IGP here. We are using, because now it's MPLS traffic engineering, we as network engineers were able to define which path is the best path for the customer. And remember, this is the customer could come and tell us, I want to use a path that has low latency. We give them that. Or I want to use a path that has 10 Mbps. We give them that. If this is 10 Mbps, and then this is 5 Mbps, this is 5 Mbps, maybe this is 20 Mbps, this is 30. So if the customer says, I want to use a path that is 10 Mbps and above, definitely we will not be using this particular path here because already it falls short of what the customer requirements are. But you see, maybe this is the IGP's best path. But with traffic engineering, we're able to define our own path and say, well, you want that particular requirement, then you will use this particular route all the way to your destination. So the most important messages in RSVP TE, again, I encourage you to read more about this because, to be honest with you, MPLS is a topic that cannot be covered in 2 hours or in 3 hours. If you really want to grasp MPLS from the basic all the way to the advanced knowledge of MPLS, you really need at least, I'm not saying you learn every hour, but you need at least 10 or more hours of study and research. And so this, whatever I'm giving you is just a foundation, just to encourage you to read more. I believe there's a lot of literature out there that can be able to help you understand MPLS, either videos or even PDF or even slides like these ones. So how RSVP works, I'm not be able to touch it intimately, but I'm giving you a high level overview of how it works. So the path setup is that is RSVP signals between ingress and egress. Using now the two most important messages here are path message and I think I got this wrong. So it's supposed to be rev. I think it's something else. I'll look up the correct one. So there's a path and I think it's RS. Can someone tell me if this is the correct one? I think so. So these are the most important messages. Then RSVP it can use to assign labels, and it can use to enforce constraint. And this constraint here, we can say we have bandwidth as an example. We have bandwidth as an example. So if a particular path does not meet a particular bandwidth requirement, then when you're trying to establish an LSP along that path, it will fail. It will fail. And this is what will happen. This is what will happen when you try to establish a path that does not meet that particular requirement. If you go to France P real quick and say show MPLS traffic engineering tunnels, let me even put which one should I do? Let me see if I have this. I don't have. I think it's tunnel. Oops. Oh, finally. So when you go to, if you issue this command in Cisco, and you've configured an explicit tunnel that does not mean specific constraint, what will happen is up here, the tunnel will be valid, and it will tell you. Anyway, let me just do that. Do show IP explicit path. Jesus Christ. Guys, just bear with me. I think I've been talking for a long time, and good. So conf t, let's go and mess up with this particular explicit path. And we see IP explicit path name, this guy, and then you say no. I want to remove this particular IP address here. Say no index 2, for example. So our tunnel will go down. I'm hoping it will go down. It takes a bit of time before it goes down. Come on, where does it want to fail me right now? There you go. So our tunnel is down, which means if we go back and give, you see earlier, admin status was up, operation it was up, path it was valid, and signal was connected. But now, if we give this command again, this is what will happen. Admin up, yes, but operation wise it's down. Path not valid, signaling it's down. Now, the good thing is this one, it tells you why this signaling is down. It's down because the path here is not valid. Therefore, what you do is you just I'm not sure if this will work. You just go ahead and reissue this IP address, and it should be able to work. So our tunnel will come up, and then of course you go back again and issue the command show MPLS traffic engineering tunnels, tunnel 10, and then we are back up here, and it will tell you for how long it has been up. Here it will tell you for how long it has been up since the last change 14 seconds ago. So basically that's what this particular point means: constraint enforcement, e.g., bandwidth and any other constraint that you've set up. So components of an LSP, as I said, an ingress LSR is also known as head-end router. Transit LSR, these are basically the provider or the P routers, and they are basically the core routers. Egress LSR is also known as the tail, it's supposed to be as tail end router. Now, ingress and egress LSRs are always the PE or provider edge routers, meaning these ones here. These ones here are what we call egress or ingress, depending on where traffic is coming from. They're always the PE the transit LSR, that is label switch router, are always the PE routers, or in some cases, you may find that, let me go back here and add, a PE router here. You might find that we have another PE router here that connects to this PE device, and you want your traffic to come this way and then go this way, then come this way before it exits out this path. Therefore, in this particular circumstance, this particular PE device becomes a transit LSR. That's why I've been able to capture the same here and say that transit LSR are almost always the PE or provider routers. This is because there are cases where provider edge routers can also play the role of a transit LSR, and I've just shown you with the help of that diagram. Right. Lastly, we have the practical use cases of label switched paths. How can we use these paths? Number one, we could actually tell or configure an LSP and tell it that you only allocated 1 Gbps of bandwidth, not more, not less. Okay, or you could even tell it that you only allocated about 100 Mbps, depending on the requirement that we have. So that's how we can use an LSP. Now, in so doing, we can also configure an LSP to avoid links with high latency. So you can say, for example, if this particular path here has high latency, please don't use it. Instead, use this path that does not have high latency. That is the practical use case of an LSP. Another one, you can use LSP to load balance traffic across multiple routes. Now, load balancing here, I'm not saying that for the same customer, you come and say that, for example, here, you come and say, for customer, this is customer A, site 1, this is customer A, site 2, this is customer B, site 2, sorry, customer B, site 1, customer B, site 2. So, and come and say this customer, when traffic comes to this PE, what happens is another traffic should come here, and then another one should come here, and so on and so forth. Like the way we have equal cost multi-paths in OSPF. That's not what I mean. What I mean is, by this point, is that you are able to ensure that there's no link that is over congested, for example. Meaning, if this customer decides to use this route for their traffic, okay, you can decide to use a different path for this customer. You can configure that so that at the end of the day, you don't have traffic going across a particular LSP and therefore congested, because that will not be very ideal when it comes to your customer requirements or what you want to achieve within your network. So basically, that's what the practical use cases of an LSP, and that's why you can actually configure. You can take this as a reason as to why you can configure LSPs when you're doing traffic engineering. Now, the benefits of MPLS traffic engineering is that you get path optimization. Basically, you avoid congestion, and then you can allocate resources. Like I said, you can reserve bandwidth and say, this particular LSP, I've reserved 1 gigabit per second or 100 megabits per second based on your requirements. And then there is QoS enforcement. Remember, the MPLS header has 8 bits, has 3 bits specifically assigned for QoS. And then, of course, you've spoken about load balancing, meaning you ensure that the way you configure or the way you manage your MPLS network, there is no over reliance on a particular route. So you're able to balance traffic within your MPLS core. And of course, there is resiliency and redundancy. So what this point means is that for customer A, we can configure this as customer A's primary path, okay? And then we can configure this as its backup path. So in the event that there is a break here, then traffic can use the other path as we work to resolve this path here. Basically, if you go to the lab that I've been using here, real life scenario is that if this customer here, its primary path is to go through PE1 and then go to PE2 and then go to P04, then come to P06. That's the primary path. But assuming there's a break here, using MPLS the fast reroute feature and backup, you can be able to ensure or achieve redundancy by configuring a primary path, which will use this particular path here. This particular path here to be able to reach this customer. So when you do that kind of configuration, what you're able to achieve is redundancy and resilience. And with that very long session, I have to say, in the interest of time, that there are some concepts that I did not really explain them very well, but I'm hoping these slides and you taking the initiative of doing more research and reading more about MPLS will be able to help. My task here was to be able to take you through MPLS so that you can know which areas you should focus, its benefits, when to use it, when not to use it, what it offers, and I've tried to be practical about it. I know this was a theory, but I've tried to be practical about it. I'm hoping the content that I've been able to share with you in the 46 slides will be helpful, or will help you whenever you're dealing with the MPLS, or more importantly for the students, my fellow students in networking, those who are still studying and getting to know how networking is done, or all about networking. I'm hoping I've been able to be of great help. And I want to thank you for giving me the platform, Martin, and for the audience for attending. I think we come to the end of the session. Now we can take, I think we have questions, Martin.
Yes.
Now we can take questions. Let me stop sharing.
Yes, David.
So we can go to the question.
Thank you so much
Yeah.
for that session. I think we've all learned a lot. And guys, let's just again clap for David using the emojis, because he has done a very good presentation.
Thank you so much, guys. Thank you.
Appreciate him again. We've all learned a lot, and we appreciate you taking your time to make the presentation, to take up that topic. MPLS is a very complex topic, and doing it in less than 3 hours, that is fantastic. And let's get the questions from the team. I know Arsenal fans are running out of time, but let's just get some few questions from them,
then we can go.
we can let them to.
We are waiting to take the lead.
Okay, Elisa,
Evelyn, thank you so much. It's RSV message. Thank you so much for that confirmation. Right. Questions,
let's
Martin?
start with Elisa. I saw the hand for Elisa.
Oh yeah. Elisa, talk to me.
Yes, Brother David.
Yeah.
Hello?
Yes, you're audible.
You can hear
Go
me?
ahead. Yes.
Yes, it was a very good session. Thank you so much. Before I ask my question,
Thank you.
right? And you see, I know that MPLS, deploying MPLS, of course, anyone can deploy MPLS, but it's a very complex network when it is deployed, when there is something like something happening, like traffic issues, not going, customer issues on the network, and to troubleshoot, and it become a bit complex when it comes about MPLS. So, um, so what an advice is, if you see that you are a small network, it's better just to stay on traditional forwarding, or MPLS is better because of latency. At least if customer want low latency, and you can provide MPLS or something like that.
Martin, would you like to answer Elisa in a different
Yes,
version?
I think you already explained the benefits of MPLS. And Elise, I don't think MPLS will fix your latency issues. And when you
No, it
are
will not.
evaluating the network of the customer, that's when you should evaluate whether you are using whether you should deploy MPLS or not. Again, it's not just about one benefit. There are many other benefits that MPLS will bring into your network. It may be a small network right now, but you're looking at the future. In the next few months or next few years, the network will grow. So if you are looking at a network that will grow and expand, you can just start it with MPLS. It can be a small network, but you can start it with MPLS. So as David explained, it purely depends with the requirements of the customer. You look at the requirements, you look at the future growth of the network, and then you are able to make a decision whether you should deploy MPLS or not. And then you look at the advantages. There are many advantages of MPLS. We've talked about traffic engineering. Maybe you are multi-homed to multiple service providers and you want to bring in the benefits of MPLS. So you can consider it based on the network requirements of your customer. Elisa,
Thanks,
are you
thanks,
present?
Martin. I think that's
Yes, Brother Martin, I understand.
that should be very okay. Okay.
Yes, we can move to Ali.
Oh, thank you again, David and Martin. You have done a very terrific job. Thank you for allowing me to speak. Uh, I can't help but notice that there are similarities between traffic engineering and typical IPSLA. I've used IPSLA in Cisco before, but the way you described it is more complex. Like it's not more complex as in configuration, but more complex as in more attributes that you can take into consideration. Where IPSLA, if this then that statements can be arranged in some way to manipulate some routes so that you can take advantage of you can change the paths of the traffic based on if statements, like in programming. But I think the way you described it is intriguing. Uh, uh, it needs more time. I need more time to fully understand it and perhaps do a lab on my own. That takes me to my question. Can you share like a blueprint for your lab so that I can recreate your lab on my own PC, please?
Sorry. You want me to share the blueprint?
Yeah. If there's any guide or blueprint that you have already, I know it's a big ask, and thanks for your time. I know you've already taken a lot out of it, but if you have anything ready, you can share it with us. Otherwise, it's okay. Feel free to share whatever you deem favorable for us, please. Thanks.
It's fine, Ali. Thank you. Thank you so much. Okay. Oscar says in the chat that I would like to have lab based on those practical use cases. Definitely. Oscar, this is something that we'll also have to arrange with Martin based on availability. And then now we'll come and do a lab about MPLS, and we'll also be able to do L2 and L3 VPN and show you a different how you can leverage the use of L2 VPN um, um, to steer away from the normal way that the literature out there is telling us to use L2 VPN. So I would leverage the use of L2 VPN in another way, and I'm really looking forward to that session. So yes, we will we'll have that lab, and hopefully we'll have as many of you joined that particular one also.
Hello, David.
Yes, I listen. Martin,
Uh,
do you have any other questions? Oh, Martin, South Africa.
yes, 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 David. Uh, requesting permission to address Elise Tomei.
Okay.
So, so Elise, when the best advice that I can give you when it comes to building a network, if you are a small service provider and you want to expand, like what Martin said, so when you are a small provider, you can have a set of PEs. But when you have a set of PEs, you don't need the provider routers because you're a small provider. The only time you add provider routers is when you want to aggregate your PE routers. So you can first start with your provider edge routers, and then as you grow, you can add your MPLS aggregators, which is your provider routers. I hope that answers your question there.
Yes, yes, I understand, Brother Martin. I understand.
Any other
Okay.
question,
Uh,
guys, before we can close the session? Any question, any comment, any feedback? It's all welcome. Anyone before we
So,
close the
yes,
session?
yes.
Yes, Martin.
So David, again, my man, well done. I have learned a lot from you, my man, honestly.
thank you. Thank
So
you.
what I can say as an enterprise network engineer from a SD-WAN perspective, it may look like SD-WAN is a MPLS competitor. Well, yes and no. And let me explain why. From an enterprise perspective, although yes, the business can say, hey, let's move away from MPLS. It's quite expensive. The challenge is if we just rely on the direct internet access. You basically going for a path that will not always guarantee that you will get to your destination. Let's say you as a provider, I give you my traffic, and then you port that traffic to another provider. You have no control of what that provider will do with that traffic, especially with your critical traffic like your voice. So when it comes to the voice traffic in the SD-WAN, the MPLS is gold. So never think that SD-WAN will will um will decommission MPLS. No. So what we do is we can have a policy within the SD-WAN that stipulates that voice packets must specifically use MPLS, right? And then when it comes to your PE, of course the layer 3 traffic you will not see because it's in the tunnel. But what you will see is the quality of service marking, because that will not be encrypted. What's encrypted is the layer 3 packet. And then what we can do is we can say, okay, Mr. Provider, when we send traffic to you and when we ask you to prioritize it, we will then perform a DSCP rewrite. So you will say, Martin, if you bring, let's say AF11, for example, what I will do, I'll say traffic that's coming from the LAN of my SD-WAN fabric. If it comes in, I will mark it as EF, but when it comes to you, I will then rewrite it into AF11. Then that AF11, you mark it from a layer 2 perspective, and that's how I prioritize it. So MPLS will remain gold within the SD-WAN, and when you do it that way, it then becomes a hybrid solution. Yeah, that's all I can say. But thank you for the session, man. I've learned a lot from you.
Thank you so much, Martin, for the input also. I would like to say here that the two Martins helped me prepare for this session. So shout out to them for your guidance and patience in trying to ensure that this session is a success. So, and for all of you, thank you for joining and thank you for the encouragement.
Thank you so much, David. We appreciate the effort and energy in doing this. We've all learned a lot, and we look forward to the next session where we can dive into the lab and now build and break things using MPLS. I hope maybe next time we can start maybe at 1:30 or 1 so that
yeah, because the lab itself, honestly, yeah, like I said, you can't do, there's very little you can do in 2 hours or 3 hours. Yes. But I'm hoping that we can get some very good time to do the lab, because as I said, we'll have to configure L2 and L3 VPN, and that isn't a small task, because I would want to configure MPLS from scratch, so that everybody can be able to know how it's done. So that's what the two Martins, you've seen the lab, and it's a very good one.
Yes,
it's ready. It's ready. It's ready. Just waiting for the day that God will allow for us to have that session. So
definitely, let's plan for it after this, and then we can communicate for the guys to be ready, and we are looking forward to it.
Yeah.
Thank you, guys. You can now go support Arsenal, PSG. I know if Manchester.
I mean, PSG, of course. I mean, it's PSG today.
Yeah, you can now go and support PSG, Arsenal, but don't touch the network. Just stay away from the network. Let's enjoy the game and then enjoy the rest of the weekend, guys.
Thank you, guys, and all the best. See you soon.
Thank you. Thank you, David.
Thank you, Martin.
Thank you, Martin, for this session. Thank you, David.